Problem number 4 reads, a daredevil is shot from a cannon with a speed of 55 meters per second at an angle of 70 degrees above the horizontal. A. What is the maximum height reached? B. How long does it take to reach this maximum height? And C. What is the velocity, both magnitude and direction, of the daredevil at t equals 8 seconds? All right, let's take a closer look at our daredevil. Here's our circus performer shot from the gun. Rises, falls back, lands safely in the net. When the cannonball emerges from the gun, we're told it has an initial speed of 55 meters per second angled at 70 degrees with respect to the horizontal. That can be broken up into horizontal and vertical components. The problem is to find the maximum height that the human cannonball rises to, also the time at which it reaches that maximum height, and then the velocity after 8 seconds. Let's assume that 8 seconds occurs about there, and our daredevil has some velocity v at that point. All right, that is our problem. Take a crack at that problem before watching its solution. Here is our problem diagrammed. I have first of all found the x and y components of the original velocity. v0x being 55 cosine 70 degrees, that turns out to be 18.8 meters per second. v0y is 55 sine of 70 degrees, that turns out to be 51.7 meters per second. I've also placed the origin of our coordinate system to coincide with the emergence of our daredevil from the cannon at t equals 0. I've allowed y0 to be equal to 0. I've also written the value for the acceleration of gravity, that is minus 9.8 meters per second, the negative sign indicating that it is downwards, adopting the common convention that quantities measured upwards are positive, those downwards negative, those measured to the right positive, those to the left negative. In Part A, we are asked to find the maximum height that our daredevil rises to. At the maximum height, the daredevil's upward motion stops for a moment and then it starts down again. And at that point, we can write that the velocity in the y direction is momentarily 0, so we can add that to our list of quantities that we already know. If you examine the equations for projectile motion, you find the equation v sub y squared is equal to v0y squared plus 2 times the acceleration times the displacement y minus y0. In Part A, what we are looking for is y. We're looking for the value for y, which we're calling h, at that moment at the top of its motion when the value for v sub y is equal to 0. So in this equation we know v sub y, we know v0y, that is 51.7 meters per second. We know the value of g. We're looking for the value of y. So if we solve this equation for y, we find that y is equal to v sub y squared minus v0y squared, all divided by 2 times g, and giving ourselves a little more room here, we continue that y, plugging in some values. V sub y, 0, minus v0y, 51.7 meters per second, that quantity squared. Divide all this by 2 times g, which is 2 times minus 9.8 meters per second, The value that you should get for this is 136 meters. That then is the quantity that we called h. In part B, we're asked for the time at which it reaches this maximum h. Again, if you examine our equations, you look at the equation v sub y is equal to v0y plus g times t. In this equation, we know v sub y, that's 0. We know v0y. We know g. We do not know t. If we solve for t, we have that it is equal to vy minus v0y divided by g. And plugging in our values for that, we have the t then is equal to v sub y 0 minus 51.7 meters per second divided by minus 9.8 meters per second. And if you run this through your calculator, you should get a value of 5.28 seconds for that time. Well, that takes care of two of the questions we were asked. The third question was to determine what the velocity of the human cannonball was after 8 seconds. Let's suppose that 8 seconds occurs about here. 5.28 seconds at the top, twice that to come back down to the ground, so somewhere in here, and that the velocity that we're looking for looks something like that. We want to know its magnitude and its direction. If we break this velocity up into its components, it would have an x component, v sub x, which happens to be v0x. Remember, that does not change for projectile motion. It would also have a component v sub y. Now, the value v sub y does change, and we have to calculate that. We can do that using exactly the same equation that we used in part B. V sub y at any time is v0y plus gt. Well, let's use that. Get a little space here, right, for part C. V sub y is v0y plus gt, and that is going to be equal to 51.7 meters per second plus g, which is minus 9.8 meters per second, multiplied by the time, which is 8 seconds. If you calculate that, you will get a value of minus 26.7 meters per second. So that the downward component v sub y then is 26.7 meters per second. Find v now. We can use the Pythagorean theorem and write that v is the square root then of our x component, which is still 18.8 meters per second squared, plus our y component squared, minus 26.7 meters per second. Square that. And if you carry out this operation, squaring, adding, and then taking the square root, you should convince yourself that you get a value of 32.7 meters per second. That's a positive quantity. It's the magnitude of this. The angle theta, let's take a look at what that angle is, first of all. Let's say it's this angle here. between our vector and the x-axis. The tangent of that angle is the side opposite the angle, which is v sub y, divided by the adjacent, which is v sub x. So going back to here, we write that theta then is equal to the inverse tangent. It is that angle whose tangent is the y value, which was 26.7 meters per second, divided by 18.8 meters per second. The units will cancel. This turns out to be tangent minus 1 of the value 1.42. And if you find the arctangent of that, you should get that this is 54.8 degrees. So that's our magnitude of our velocity at 8 seconds. That is the angle that it is made with the x-axis, and we have now completely solved our problem. All right, let's move on to another problem.